This is the part 5 of our small series on bind 9 management. And today we follow up from last time's webinar where we talked about dynamic DNS. This time we look specifically on dynamic DNS update security with the update policies. We look at Tseg security and catalog zones. So yeah, already talked about that. First topic I would like to talk about is the transaction signatures, or Tseg. Now, Tseg are or have been defined long ago, like 20 years ago, but they have recently been updated in RFC 8945. But yeah, don't get you spoiled with the high RFC numbers. This is just an update RFC, so Tseg is actually quite old and well established already. We can use Tseg to secure communication in DNS between two endpoints. And these endpoints can be used for different DNS communication. It could be a server talking to a client, it could be servers talking to each other, and it could be an updater, like the NSUpdate tool talking to a DNS server. When we use Tseg, we use an hashed method authentication code, or an HMAC, so it's symmetric encryption. And there is trust required between all the systems and all the endpoints that talk Tseg. So this is different from like DNSSEC, where we have public and private keys, and where we don't need explicit trust between the communication parties. With Tseg, we need that. Also, because Tseg encodes timestamps in the hashed method authentication codes, all the endpoints that communicate with Tseg must have reasonably accurate clocks. So it's a good idea to have them synced over the network, for example, with the network time protocol. Tseg, while being developed roughly at the same time as DNSSEC, it's completely independent from DNSSEC. So you can use both together, but you can also decide to either use Tseg or use DNSSEC. And we will cover Tseg in more detail here. So the use cases for Tseg are that we can have dynamic updates that we secure with transaction signatures. That is between a Tseg, a dynamic update client, which could be an operating system client or could be a DHCP server, and an authoritative DNS server. Tseg is also used to secure the server control messages in bind. So if you use RNEC to send control commands to your bind server, that control commands are also signed with Tseg, and the server authenticates the RNGC tool with that key. We can secure server communications like zone transfers, notifies, and normal queries between servers. And also, it is technically possible to secure the queries that the client sends to a server and also the responses coming back from the server to the client. However, because we need mutable trust between both endpoints, that is impractical and rarely used. So technically, the Tseg is an extra resource record that we will find in the additional section of a DNS message, both in a DNS response and a DNS query message. And it looks like a normal DNS resource record. However, we only see the Tseg record on the wire. We don't see it in a zone file. Also, Tsegs are never to be cached in a cache because they have always a TTL, a time to live of 0. And the Tseg actually contains a hash and additional information that is or can be used by the recipient to check the integrity and the authenticity of the DNS message. So with Tseg, we know, or the recipient know, that the message is coming from the correct sender which is a sender that has the same Tseg key configured, and also that the message hasn't been tampered with during transport. So here we see Tseg operation in one picture, and we start at the top left, where we have the plain text that we want to secure, which normally is a DNS message, which could be a DNS update message, could be a zone transfer, something like that. And we combine that with a pre-shared key. And then both the plain text and the pre-shared key is being given into a cryptographic hashing algorithm. In this example here, we use HMAC SHA-256, and that creates a hash value. And then the plain text message is being sent with the hash being stuffed into the Tseg record, into the additional section of the DNS message, and is sent from the sender to the recipient. And then on the recipient side, the recipient takes the plain text and takes its copy of the pre-shared key, which hopefully is the same one than we see on the sender side, and also applies the HMAC SHA-256 cryptographic hashing algorithm to the data, and out comes a hash value. And then on the recipient side, we compare the hash value that we compute with the hash value that we see in the additional section. And if both are identical, we have proven that this message must come from a sender that is also in possession of the same pre-shared key, and also that the plain text, the data that has been sent, has not been changed between the sender calculating the hash and the recipient calculating the hash. So it has not been changed in transit. With Tseg, we can use different HMAC algorithms. And for a long time, Tseg has been used with the HMAC MD5 algorithm. However, MD5 has shown some weaknesses and is nowadays deprecated. We shouldn't use that anymore. The same is with the SHA-1 algorithm. Instead, we use what's called the SHA-2 algorithm family, and the one that is most popular and most often used is SHA-256. However, if you like, you can even go up to SHA-348 or SHA-512. Depending on the algorithm, when we calculate a cryptographic hash with a cryptographic hashing algorithm, we take random length input, which is the DNS message that we want to secure, and we create a fixed length fingerprint. So your DNS message will be larger by that amount, plus some metadata that is being required for the Tseg record itself. And you see here that for SHA-256, we have an extra of 32 byte. And with SHA-512, we have 64 extra bytes. When we use bind, we have different ways to generate that Tseg keys, which are the pre-shared keys required to sign DNS messages with the Tseg algorithm. We can use RNDC confgen to create a Tseg key for the remote control channel for the use with RNDC. And then we have DDNS confgen, which is designed to create keys for dynamic updates and for NS updates. And then there is Tseg Keygen, which is a generic tool that creates Tseg keys that we can use for all kinds of purposes in bind. We can even use them for RNDC or for dynamic updates. So here's an example how to create a Tseg key. Tseg Keygen was first introduced in bind 9.10 and should be available by all commonly used bind installations nowadays. So you call Tseg-Keygen and you give the name of the key as the first parameter. Optionally, you can select a different hashing algorithm if you like to. If you don't do that, it will default to HMAC SHA-256. And then it prints out the new key material on the screen, on the terminal, and you can copy and paste or redirect that into a file. Be careful here, whenever you execute that command, even if you execute that with the very same parameters, you always create a different key, because a key is being seeded with random data. And sometimes in the DNS trainings that I give, I see people that execute this command on one machine that they want to secure with Tseg, and then they execute the very same command line on the other machine, which they want to secure. But of course, if you do that, you will end up with two different keys and they won't match. So what you need to do is you create the key on one machine and then you copy over that key to the other machine where you want to secure the communication with. So if you create Tseg keys for the remote control daemon for RNDC, it's best to use the RNDC confgen command, because that also automatically creates additional configuration information for RNDC. And there's even the RNDC-confgen -a parameter for automatic, which just generates the key in a well-known file that bind will pick up, and also the RNDC command will pick up. And it's the easiest way to configure RNDC. If you want to use Tseg to secure zone transfer, then you create the key, you copy the key into your bind configuration file, into namely.conf, and then you specify the key in the allow transfer statement of a zone file. And that will allow zone transfer for every secondary that can provide the same key, basically that is configured with the same key. It's important here that keys must be configured before they're being used. So have the key statement before you use the key in the zone statement. Don't copy a new key just at the end of the zone file. Best is to have them somewhere in the beginning of your configuration file. Also, the keys must be configured on both sides, on both endpoints. So you need to have the key on the primary server and also on all the secondary servers. And here's the copy for, or the configuration example for the secondary server. We have the very same key here, and then in the masters clause we have the IP address of the master server, and then important, there's no semicolon after the IP address. It is directly followed by the statement key and then the name of the key as defined in the configuration file, and then the semicolon that terminates this configuration for one primary, and then you can follow with more IP addresses and more keys if you have maybe multiple primaries, which is possible.
Hey, Carsten.
Yes, please.
Could you go back to the last slide for a sec?
Yes.
I'm sorry to interrupt you, but someone asked a question that I think you could answer just looking at this slide. So the question is really about how do you transition from one algorithm to another? Can you add multiple keys for that IP address? So you've got under masters, you've got the one IP address and one key with one key name. Can you add others in there, or how do you transition?
I've never tested this because usually that's not really required. Usually what you do is just create a new key and change the key on both sides.
I think the question was really about how do you transition from one algorithm to the other. So I guess what you're saying is you just do it quickly.
Yeah, I mean, for zone transfers are usually not that time sensitive, and even if the zone transfer is not working for 5 or 10 minutes, usually in most instances that's not a big problem. So you just create a new key with the same name but with a different algorithm, and then you copy that to all your secondaries, and once the key is in place and the configuration is reloaded, all the secondaries will then start doing the zone transfer. However, if a timeout of, or not a timeout, if zone transfers are not working for like 5 or 10 minutes, if that is not acceptable, then something else must be done. I've never been in this situation, so I've never tested if it is actually possible to have multiple IP addresses with different keys. It might be, but I don't know.
Someone has commented that it is. Sorry for the interruption. Keep going.
No problem. So it's even possible with Tseg to secure all communication between two DNS servers, to bind DNS servers, that is, if you specify on both sides a server statement with the IP address of the other endpoint. And then inside the server statement, you give the key statement with the name of the key. And that will Tseg sign all communication, which includes just normal queries like queries for SOA record, which includes the notify messages floating around between the servers and also zone transfers. And that is like a catch-all between one or more servers. So if you have one primary server, multiple secondary servers, you can have just for every server such a server statement, and then have the keys in there, and all the communication between your servers will be automatically Tseg secured, and there's no need to have then other explicit configuration in the bind configuration file. In this webinar, we look specifically on dynamic updates. And last webinar, we have seen how dynamic updates work. We have used the allow update statement, and we've used allow update with IP addresses. Now, IP addresses provide only a weak security because the source address of UDP-based DNS messages can be spoofed quite easily, actually, and there's no way of the recipient to figure out that the address might be spoofed. So it is recommended for better security to use Tseg keys instead, having access control list based on only IP addresses. Because if you enable dynamic updates on a zone, if an attacker can spoof the source IP address, that attacker can make unauthorized changes to the whole zone content. And that can be really, really dangerous, especially if there's no monitoring in place and you don't see the changes happening. So how do we use Tseg with dynamic updates? We first have the Tseg key defined in the binds named.conf file. And then in the zone block, inside the allow update statement, we replace the IP address with a statement key and then the name of the key we want to use. Now, it is possible to just have one global key that will secure all your zones. However, then you have all the eggs in one basket, and if that key leaks, if that key becomes public knowledge, then all your zones are vulnerable. For better security, it's recommended to have one key for each zone, or even some people have one key for every communication between a primary and a secondary. So if, for example, there's one primary and 3 secondaries, they might have 3 different keys, one for each communication between the primary and the secondary. But usually having one key per zone is secure enough. So we have seen that we can use Tseg to upgrade the security of dynamic updates and other communication of a bind name server. However, with the allow update statement, anyone that is allowed to make changes to the zone, that is anyone coming from the right IP address or anyone having the correct Tseg key, can make any changes to the zone, can update the whole zone, can change the ZOA record, can change the NS record, can change all the A record. And that might be too much power for some people, at least. With the update policy statement, which is mutually exclusive to allow update, we can have a more fine-grained access control for the dynamic updates. With update policy, we can either grant or deny a specific identity, which is a Tseg key, the change of specific resource record. And we can specify these resource records either by domain name or by record type or by both. That means domain name and record type. And I will go deeper into how that works. So the syntax of update policy is that we have the keyword grant or deny. So we either allow or we disallow change or updates to a specific resource. And then we specify the identity, which is the name of the Tseg key. Then we have a match type, which we will cover in the next slide. We have the target name, which is the domain name or can be the domain name of the record that can be changed. And then optionally, we have a list of resource record types that can be changed. So first, let's have a look at the match type, which controls which domain names we can update with a specific Tseg key. And if we specify a match type of name, so literally the text name as a match type, then only the target name can be updated. So only all the records that directly match that domain name can be updated. We can specify subdomain as a match type, which means someone can make changes to all the subdomains of the target name, but not the target name itself. So if we say subdomain example.com, that means some person having access to a Tseg key can update example.com, mail example.com, and maybe zoom.example.com, but cannot update the SOA record for example.com and not update the NS records for example.com, and not the NS records there. If we want to have someone be able to update the whole zone, that would be then the match type of zone sub, which allows any changes to all subdomains in the zone in which the update policy statement appears, which includes the apex of the zone, the domain name of the zone itself, plus all the subdomains of that. If we specify zones up, we don't have to specify a target name because the domain name directly comes from the zone block in the bind configuration. An interesting option is the match type of self. With the match type of self, a Tseg key can update all the resource records where the domain name of the resource record matched the name of the key. So if we have the zone example.com and we have a domain name entry and a resource record of www.example.com in the zone, we can create a Tseg key where the Tseg key itself is named www.example.com, and that key can then update that A record and quad A record on the web server's domain name. And we can have similars, like for the name, we can have that for self as well with self sub, which means we can update the name and all the subdomains of the key name. Or with self wild, we can only update subdomains of the name. And as last, we can have a match type of wildcard, which is then a wildcard expansion of the identity. For people who operate either Microsoft Active Directory environments or Kerberos LDAP environments, in these environments, we can have rules, we can have keys that update their own domain names, which is like the default how Microsoft clients update DNS in a Microsoft integrated Active Directory DNS server, but we can do the same with a bind DNS server and dynamic update with the MS self, MS self sub, and MS subdomain match types. These will take the Microsoft Active Directory domain or the Kerberos domain and then act on that. With MS self, a client can only update its own host name. With self sub or subdomain, the client can update any records inside its own domain or even in subdomains below that. And for Kerberos, it's the same, just a different implementation. And at last, we have three special match types. The first one is TCP self, which is a little bit complicated because it allows update via TCP that match the domain name of the sender's IP address reverse name resolution. So we have to think about that sentence a little bit. So there's a client, and the client has an IP address. And the client sends an update via TCP to a bind name server. Then the bind name server does a reverse name resolution of that IP address of the client and finds a domain name for that IP address. And then that domain name can be updated. Basically, a client with TCP self can update its own domain name if the reverse name resolution actually already matches that IP address. Something similar is possible with 624, which is an IPv4 to IPv6 transition technology, where the IPv6 prefix can be automatically updated because it can be dynamic. And the last one is interesting for everyone who wants to implement their own authentication methods with external. And there is a protocol defined where bind then talks to an external daemon over the network with a specific protocol. And then the external daemon will look at the data, look at the IP address, the TC key being delivered and the domain name to be updated, and then will give a verdict back to bind to either allow or disallow that. And with that, administrators can just write their own authentication methods and authenticate maybe against an SQL database or something like that. Just for completeness, while TCP self and 624 self work over TCP, it is theoretically possible to also spoof TCP sessions. Still, it's much harder than UDP, so it has not the same weaknesses as working just over UDP with allow update. So that was about the match type in update policy. The target name is the domain name or the start of the domain that can be updated with the TC key. That target name can be a wildcard. And then at last, optionally, there can be a space delimited list of resource record, which can be updated, which are either allowed or denied by this policy. We can use the keyword any, which matches any resource record type except the NSEC and NSEC3 record, because it doesn't really make sense to manually change NSEC and NSEC3 record. These records are usually calculated inside bind whenever there is an update to a DNSSEC signed zone. And if we don't specify any record type, so if we just keep that field empty, then it matches all record types except signatures, that is resource record signatures, NS record, SOA record, NSEC, and NSEC3. So here are some real-world examples of using update policy. In this example here, the holder of the TC key named update key can change the A and quad A records of www.example.com, but nothing else. So cannot change staging.example.com. That's not possible. It's just the literal name example.com that can be changed, and only the IPv4 address and the IPv6 address. No TXT record, no SRV record or something like that. So this is a simple use case. Here we see an example of the self-match type, where we grant update privileges to a wildcard name, which is the asterisk here. So we grant any TCK that comes along that is also configured in the bind namedist.conf configuration. And any of these TCKs can change the IPv6 address of any record that has a domain name that matches the name of the key. So if someone has access to a TCK named www.example.com, and that same key is also configured on the bind side in the named.conf, that person can then change the IPv6 address of the domain name of www.example.com. And here we have an example of an update policy where a TCK named the super key can change anything at and below example.org. So this line, this configuration line, is very, very similar to allow update, because it allows for the domain to make all the changes, any records, any names, starting with example.org. So that was the update policy. Very useful and very powerful once you get your head around that. It requires a little bit testing maybe, and a little bit figuring out how update policy works. I have some links to the bind documentation where you can read more about update policy at the end of the slide deck. And now we come to the third part of the webinar, where we talk about automatic DNS provisioning with catalog zones. Now, dynamic updates are fine to make changes to existing zones. We can create resource records in zones. We can delete resource records in zones. And by deleting and adding new records, we can make even changes to zones. However, with dynamic updates, we can't create new zones and we can't remove zones. And this is where catalog zones come in. So if we manually create new zones or delete new zones, we have to log in into the primary DNS server, create the zone, and populate just a rudimentary zone with an SOA record and NS record. And from that, we then can start using dynamic updates. And we need to log in to all our secondaries and create the secondary zone there, which is quite a lot of work if you do that on a regular basis. Of course, administrators use tools to automate that, either simple shell scripts or some provisioning tools like Ansible or SaltStack. But there might be an easier way, and that easier way is catalog zones. So a catalog zone is a normal zone that keeps track of the catalog of a DNS server, and RC 1035 defines the catalog of a DNS server as being the list of all the DNS zones as DNS server is authoritative for. Catalog zones is a creation of ISC. It has been introduced in bind 911 in 2016, and it's been currently standardized inside the IETF. There is an internet draft, which is an RC standards document work in progress, and it's linked here. It's called DNS Catalog Zones, and the last version is from February this year, but it's very much still work in progress. So you can't currently read that draft and get everything. So I at this point of time recommend to read the bind documentation, which explicitly documents how the bind configuration work. And it seems to be that the IETF implementation will differ a little bit from the initial IC way of catalog zones, and bind will then adapt once the RC will progress. In addition to bind 9, The not DNS authoritative server already has a fully functional implementation since version 3, which came out in September last year. And PowerDNS has a proof of concept external program called PowerCats for catalog zones that can be used to augment a PowerDNS authoritative server with catalog zones. And then I've seen on GitHub a couple of Python scripts that can be used to add catalog zones to just almost any authoritative DNS server out there. So a catalog zone, first of all, is a normal DNS zone. It has SOA records, it has NS records, and for all use and purposes, it just feels and works like a normal DNS zone. It is maintained on the primary server, like all normal authoritative zones are, and it contains the zone names and configuration metadata of all the zones that should exist on the secondaries. And for all the zones that we add to the catalog zone, these zones will automatically provisioned on all our secondaries. So the catalog zones is being transferred over to all the secondaries, and because the catalog zone contains the configuration metadata about the zone, then the bind server that runs on the secondaries will automatically create the zones, and then we can start managing the zones by dynamic updates, for example. So in order to be able to use catalog zones, and because the primary DNS server hosting the catalog zone has just a normal zone, it can be actually any server. It doesn't need to be a bind server, or it can even be an older bind server than bind 911, if that makes sense. Usually not, but technically it could be, because a catalog zone is just a normal zone. On the secondaries, there we need a special DNS server that knows about catalog zones. So on the secondary side, we will need to have bind 911 or later. So a 912 or 916 or 914 to work with catalog zones. So the catalog zone on the primary can be a static zone, so a zone managed by a text editor, or it can be a dynamic zone. From my point of view, having the catalog zone as a dynamic zone really makes everything automatic. But if you, for some reason, you don't want to use the catalog zones with dynamic zones, you can do that. You can have the catalog zone as a static zone. And there's no special requirement for the configuration nor for the name of the zone. However, it's recommended that you choose a name for your catalog zone that doesn't collide with any domain name used in the network, neither in the internet nor in maybe your private DNS namespace. A good idea might be to just pick a name which is a subdomain of an internet domain that you own and use that for the catalog zone. And here in our example, I've used catalog.example.com as the name of the catalog zone. The catalog zone itself is never seen outside the authoritative server. So it is not queried, it's not been resolved by by a resolver somewhere in the internet. There also doesn't need to be a delegation for the catalog zone. It's just purely internal to the authoritative DNS servers. A catalog zone has a pointer record for each member zone. That's the way how the member zones, the zones that are being managed by the catalog zones, are being registered into the catalog zone. The pointer records point from just like an index name that needs to be unique, which is on the left-hand side of the pointer record, to the real zone name on the right-hand side. The reason for this pointer record is that on the right-hand side, we have no domain name restrictions, while on the left-hand side, the name must be inside the zone name itself. So if our catalog zone is named catalog.example.com, the left-hand side name must end in that name, while on the right-hand side, we can have just arbitrary names. And that is what we want in the management. We want to manage any name, any zone. Also, the catalog zone on the primary requires to have a TXT record with the version number of the catalog zone protocol implementation. And the catalog zone protocol implementation, as we have it in bind 9.11, is the version 1. And if the TXT record is being omitted, then version 1 is always the default at the moment, at least. And then there's version 2, which is the catalog zone protocol as it is described in the internet draft and as it is implemented in bind 9.16. Because they are now two different implementation, the bind server or any other DNS server can read the TXT record and find out which version is actually being used. A DNS server should ignore all catalog zones that have a version number that it doesn't support. So a bind 9.11, if it sees version 2, will just ignore the catalog zone and will not act upon it, because 9.11 only supports version 1 of the catalog zone implementation. Here we see the content of a catalog zone. It has a SOA record. It has NS records like any normal zone listing the primary and all the secondaries, and it has one TXT record with the version number. On the secondaries, in the named.conf, we specify certain zones as being a catalog zone. So we register in the bind configuration a specific zone name as being a catalog zone. And that's being done in its own catalog zones block, which lives inside the option block. And the configuration for the catalog zones is what we see here in red. So we specify here the zone with the name catalog.example.com as being the catalog zone. In this case, it's not an in-memory catalog zone. An in-memory catalog zone is a zone that is not being saved to disk. It's like a secondary zone that has no file statement. It's only being managed in memory. And when the bind server is being restarted, all the state and all the information is gone, and it will be fetched again from the primaries. The zone directory specifies in which file directory on the file system new zones should be created. In this case, it's the directory cut zones, which is relative to the home directory of the bind name server. And then we can also specify default primaries, which are the IP addresses of the primary servers where a new zone is being populated from. That is, from that IP addresses, we can do the initial zone transfer, which is usually the same primary server where we get the catalog zone from, but could be also a different one. And then below, we have the definition for the catalog zone, which is a typical just normal secondary zone configuration, which is there in order to zone transfer the catalog zone from the primary to the secondary. So now we have the setup. We have an empty catalog zone on the primary. We have the catalog zone on the secondaries configured, but the catalog zone currently is empty. In order to provision a new zone inside the catalog zone, on the primary, we create just a new primary zone or master zone if you have an older version of bind. And in this case, the zone is called catalog test example.com. And this is a production DNS zone that we want to provision to our secondaries. It's of type primary, and it has a file containing the zone content. And now that we have configured that zone and we've reloaded our primary and we tested that the zone is working on the primary, we have to register that new zone into the catalog zone. And that happens with the pointer record. And the domain name of that pointer record must have a unique name. For example, it could be a SHA-1 hash of the new zone's name, because a SHA-1 hash is reasonably unique, and it's very, very, very unlikely that that will ever clash with any other name. However, you can just also use random names that you think of and make sure that they are unique. And then we add the domain name of we add the labeled zones and then the name of the domain of the catalog zone there. So in our case, the unique name is cat-test. That's our unique name. Zones is the label that defines that this is a zone metadata configuration. And then catalogexample.com is the name of our catalog zone. So here we see the entry that we do in the catalog zone. It's cat-test.zones. And because it's not terminated with a dot, we append the name of the zone itself, which is called catalog.example.com, point a record to catalog-test-example.com, which is the actual name of the zone that we register. Because we make a change to the zone file, we increment the serial number, we reload the primary server. The primary server now detects that the zone has changed, the serial number has incremented, so it sends out notifies to all the secondaries. The secondaries get the new server record, they immediately do a zone transfer. All the secondaries that receive the zone transfer will see the new pointer record and will then automatically start to configure a new secondary zone for catalog-test.example.com. So the secondary automatically starts serving the new member zone. We don't need to log in to any of the secondaries. We even don't need to have login access to these machines. So that could be just offsite secondaries, maybe secondaries operated by some other party. And all the updates to the member zones will automatically transfer to the secondaries as well with the normal methods. So notifies, IXFR, etc. And we can add additional zones to the catalog zone. And whenever we do that, they will be automatically provisioned on the secondaries. And if we remove a zone from the catalog zone by removing the pointer record from the catalog zone, that whole zone is automatically removed from the secondaries as well. And if there is a zone backup file on the secondary, that will be deleted as well. So catalog zones together with dynamic updates make a highly dynamic way of managing a bind name server and authoritative servers with primaries and secondaries. Now we've seen that we use the pointer record to register the name. We can also have additional metadata configuration in the catalog zones. For example, we can specify access control lists. We can specify, for example, the allow transfer clause or the allow query clause and we can list the primaries for every zone inside the catalog zones. We can either do that global with resource records that then are valid for the whole catalog zone, or we can have specific metadata configurations for each zone. You find details on how to do that in the Bind Administrator Reference Manual. So here's the metadata that we can have. We can have the primaries, we have allow query, and we can do allow transfer. And we see here some examples how that works. The first red entry here is a global configuration of the label primaries and then an IPv6 address that defines that IPv6 address as being the default primary for all newly created zones. So on the secondary side, there will be automatically a primaries or master statement with that IPv6 address in there. And then we have primaries for cat-test.zones with an A record and an IPv4 address, and that is then an additional primary that is for the specific zone cat-test or for catalog-test.example.com. And with allow transfer, we define an APL resource record, and that APL resource record defines an access control list of networks that are allowed to do zone transfers. In this case, these are /32 networks, these are single IP addresses, but we could also just define whole network ranges with that. Here we have additional resources. We have the chapter on Tseg in the bind administrator reference manual. We have the dynamic update policies, and we have bind 9 catalog zones all in there. And now I open the floor for question and answers, and stay tuned because we have, as we had in the last webinar, we have a hands-on part that you can do with virtual machines just after the question and answers.
We have loads of questions.
Good.
JP has waded in and answered some of them. The first question is one no, I didn't interrupt you to ask this. Grant was asking, this is back about the Tseg keys. Is there an advantage to using a server-based key versus explicitly having a key on a zone master statement? So I think really the question is about, why wouldn't you just use server keys instead of having separate keys with much more granular permissions?
Maybe ease of management. That might be one reason that I can think of. If you have specified Tseg keys between your servers and have that globally, you don't have to think about securing every zone manually or create keys for them. So it might be easier that way. Also, if you use catalog zones, I'm not 100% sure if with catalog zones we can specify already Tseg keys if that is already in the current specs. So if you use catalog zones and you want to secure the zone transfer with Tseg, having a global configuration between your servers might be the only option right now, although I think it's being discussed in the ITF how to specify that in the metadata of catalog zones.
Okay. Philippe was asking whether you can force TCP use for NS updates.
Depends on the client or the update client functions. So you can do that as JP also mentions with NS update. You probably can't do that on the on some operating system clients. So if you want to have the operating system client send dynamic updates, possibly not possible with like Linux or Windows.
Well, presumably that's the reason for the Tseg keys in the first place.
Yeah.
So there were some questions about whether or not there was a typo in your example. I'm not going to read that question because it's I'll get typos in answer.
It's totally possible. I always create typos in there to test my audience.
So I'm looking at this question from Rick that JP and Grant have waded in on. You can look at that after people start the lab and maybe have a comment offline.
Yes.
So we already discussed the question about how do you transition from one Tseg key to another. So there was a question in your example. I think I saw this and JP's commented, but your example is using catalog zone version 1. Is that right?
Yes.
Yeah. Does using catalog zones, this is from Andy, does using catalog zones for auto provisioning in any way complicate promoting a secondary to a master?
That's a good question. Yeah, a little bit. because you have to you promote the secondary zone to a primary or master zone, and then you have to remove that zone.
Yeah, it seems like it does. It does complicate it. So I made a couple of poll questions that I'm going to pop up, but people can just answer them if they feel like it while they're working on the lab. So I'll put those up, but why don't you go ahead and just introduce the lab?